Okay, we're going to continue on here. All right, so we don't have too much further to go in terms of this chapter, which is good because it's the last one that's going to be on our exam coming up on Tuesday. So we just talked about basically osmotic pressure. And again, really osmotic pressure is still the ideal gas law. As I said before, you can either remember the other formula or just use it. And you can calculate the osmotic pressure from it. The next thing we're going to talk about is really the colligative properties that we just talked about, but all of the sort of problems that we did involved non-ionic solute. And as I mentioned before, when you have a non-ionic solute, essentially when you throw that guy into a solution, you're basically going to get a one for one sort of particles in that solution. And that is not the case when you actually have something that is ionic. Uh, when you put something ionic in there, you actually get more particles in the solution, which is a big effect on the colligative properties since, as I mentioned before, they're all based on how much particles and ions and stuff is floating around in the solution. So when we do have a situation where we have multiple sort of particles in the solution from our solute rather than a non-ionic guy is going to be one, we have to take into account what's sometimes referred to as the von Hoff factor, and that is sometimes abbreviated with an I. And the I, for most parts, represents how many particles you get per solute that you put in there. So in our non-ionic guys, basically I is equal to one, since when you put one molecule in, you get one molecule swimming around in the water. Now, if you have something that's ionic, for example, like sodium chloride, when sodium chloride goes in for a swim, it's not going to stay together. It is going to produce one and two ions per every molecule that you put in there. So you get kind of like a one for two situation. You dump that in, you now have two things floating around that solution rather than one for one. And in that case, I would actually equal two in this case. And if you have something like, say, calcium chloride, when that breaks apart, you get a calcium ion and two chloride ions. And if you were to dump that into solution, you're going to actually get a 3-to-1 sort of relationship, and I would equal 3. So you can figure out the von Hoff factor really by how many ions an ionic compound will break apart into if it is the solute rather than a non-electrolyte or non-ionic solute. How does that affect? Well, we do see this basically affect all of our uh, colligative property sort of formulas. So if you took your vapor pressure one we saw before, you could put your I factor into that. Your freezing point one, you could put your I factor into that as well. And your boiling point, you could put your I into that as well. So we can incorporate the von Hoff factor into those problems like we did previously, and we will actually put the I in there. The reason we didn't do it before, again, we had a non-ionic solute, which basically meant I was one. So basically, nothing's going to change in that case when we do that. Obviously, the more particles, the greater effect is going to have on those type of factors like boiling point and freezing point. You're going to see a greater difference in boiling point temperatures and freezing point temperatures when you dissolve something that is ionic. So, for example, if we take a look at if we had a 2 mol, say, sodium chloride solution versus a 2 mol, say, non-ionic solute solution, like sugar or glucose or something like that. Or if we have like a 2 mol aqueous solution of calcium chloride, they all have the same molality in this case. And if we were going to do this with our freezing point of 1.86 for our Kf for water, if we did it for our non-ionic one, like we did previously, our change in freezing point temperature would be technically 1 for the non-ionic, even though we don't need to put it. 1.86 degrees Celsius times the molality, and we'll take 2 for our molality here that I just made up, obviously. And that would give us a change in freezing point temperature here of 3.72 degrees Celsius. Now I take the same sort of concentration, if you will, of sodium chloride and put it in there. Our I is going to equal 2 in this case. So the change in the freezing point would be 2 times 1.86 times our freezing point constant and our 2 molal. And obviously here we're now going to increase our freezing point to change of 7.44 degrees. So because there's more particles in the solution, we see clearly a much larger increase in the freezing point depression than what we had previously. And we'll see an even larger one in this one, as I will equal 3 in this case. And if we pop that in there with our same molality, 3 times our 1.86 degrees Celsius over molality and our 2, we obviously here are going to end up with looks like 11.16 degrees Celsius. So what we see is the more particles in that solution, the more disruptive it is to the normal freezing point, and it's actually going to start to freeze at a lower and lower temperature. We would see obviously the same sort of effect with boiling point elevation. It would actually make the boiling point continuously raise, raise, and raise depending on what's in there. So this I factor is something that you sometimes have to take into account. You have to take into account it when you're dealing with something that is an ionic a solute that's being put into that solution, rather than a molecular non-ionic solute. Any questions on that there? Here is a table. In reality, if you actually measured the I value, it is slightly different than what we would predict. As you can see for sodium chloride, it's 1.9 versus 2, 1.3 versus 2. But pretty much for all calculations, you could go by just the formula and use that as your I value, obviously, rather than the measured one. They're fairly close, but there is a difference. Definitely as you start getting a lot more particles sort of involved in there. All right, so once you calculate what is the measured von Hoff factor, if we have a 0.05 molal calcium chloride solution that has a freezing point of minus 0.27 degrees Celsius, again, freezing point 1.86 here. So in this case, we're looking for the von Hoff factor, which is I in this case. If it wasn't this type of problem that you're looking for I, we definitely know that I would be involved because here our solute is ionic. So that's a good way to remember I need the I if it's ionic there. So we are doing freezing point here. So we'll use our normal freezing point formula, but we will insert the I in there because it is an ionic guy. And we have Kf and our molality. So putting in our stuff here, once again, this is the actual temperature at which this guy freezes. This, as we talked about previously, again, is not the change in the freezing point temperature. We know waters are solvents, so again, we're going to have 0 degrees Celsius. So the change in the freezing point temperature is the temperature of the solvent minus the temperature of the solution. And that's going to give me the change in freezing point temperature is 0 minus 0.27 degrees Celsius. Once again, that's sort of how we get rid of that negative sign that should not be there. And now we do have the change in the freezing point temperature. Putting that into our equation here, solving for I, 1.86 degrees Celsius molality. And they did give us the molality here of 0.05, looks like. Molality is going to cancel, and we're going to multiply these guys and then divide it to the other side. So we'll take 1.86 times 0.05. That's going to give us 0.093. And 0.27 divided by that will get us an I of about 2.9, which is pretty close to 3. And that's what we would sort of predict I would be in this case, as again, calcium chloride is, as we saw earlier, calcium ion and 2 chloride ions. And that is a prediction of I being 3, which is very close to the measured value here. Any questions on that there? So the von Hoff factor needs to be incorporated whenever you're doing any type of colligative property calculation, again, involving an ionic solute. And again, you can use the I value predicted based off the formula. That should be good in pretty much all cases. All right. Let's see here. We're going to do that one, I think. Now, to finish up here in this chapter, let's talk about a few other sort of properties of solutions. Earlier, we talked about a semi-permeable membrane, and that is a membrane that allows certain size molecules to pass through, like in cells and stuff like that. But basically, these membranes have holes in them, and the holes are small enough or large enough for certain size molecules to pass through. Obviously, bigger molecules are going to be a little problematic to kind of pass through there to get to the other side. We have colloids. These are things that are much larger than solute particles in solution. These are large molecules like proteins and groups of molecules and ions. They are homogeneous, which means they look the same throughout. They typically do not separate out or settle out. Now, colloids are small enough to pass through filters, but they are too large to go through a semi-permeable membrane. They kind of get stuck. We also have suspensions, and suspensions are heterogeneous, like mixtures, which you see different phases. So in a heterogeneous sort of suspension, you do see non-uniform parts in there. They are usually large enough that you can see with your naked eye, and they're usually too big to even go through filters, like filter paper and semi-permeable membranes. By the way, filter paper that you put like in a funnel also has holes on it that is big enough to allow certain things to pass through and not big enough to allow other things to pass through, obviously. And that's what we see here again in our membrane. These guys, solvent water molecules, no problem. But again, we're going to get kind of these larger molecules. They are definitely going to get hung up, and they're not going to be able to pass through to the other side. And you can see here, only our suspensions will settle out, which is usually why you have to mix those things. If you, for example, get a medication that's in suspension, you got to give it a good mix to mix everything together. Here you can see with a filter paper, we could get the smaller guys to sort of pass through our solutions and our colloids. And if you have some type of membrane, like a dialysis bag here, it's going to let just really small particles pass through. That brings us to, as we were talking about earlier, osmosis and osmotic pressure. Again, a reminder that osmosis is really the movement of solvent molecules from a lower concentration to a higher concentration. Again, the idea there is to kind of like dilute down the more concentrated solution to try to equal out the osmotic pressure on each side, for example, of a cell or something like that. Osmotic pressure, as I mentioned before, is basically that stop of the flow of molecules from that lower concentration to the higher. Osmotic pressure is based on how many particles are dissolved in the solution. The greater the number of particles in the solution, the greater the osmotic pressure. Pure water, which is just water molecules, have nothing dissolved in it, actually has no osmotic pressure associated with it. Another unit of osmotic pressure, sometimes people calculate it, was known as osmolarity. And osmolarity is basically your I times your molarity will equal your osmolarity. So same idea as what we were just talking about sort of with the von Hoff factor with our sort of freezing point, melting point sort of situation. If you had a 2 molar solution of sodium chloride, versus a 2 molar solution of calcium chloride. As we saw earlier, our I would be 2 in this case, and our I would be 3 in this case. And if we calculate the osmolarity, which is sometimes abbreviated as osmol, we would do it for sodium chloride, which would be 2 times our 2 molar, gives us 4 osmolarity. If we did it for our calcium chloride, the osmolarity would be 3 times our 2 molar, our 6 osmolarity. So even though these two solutions have the exact same molarity, there is a greater amount of osmotic pressure in the calcium chloride solution because there's a greater amount of particles that are floating around in that solution. So again, the more particles in there, the greater osmotic pressure you're going to have. And again, it could cause some problems depending on what's going on. And speaking of sort of the osmotic pressure on solutions, there's 3 types of solutions. There's isotonic, hypotonic, and hypertonic solution. Isotonic solution has the same osmotic pressure as body fluids, is what is used in IV fluids. And what that means is if you took the classic example of a red blood cell, which is kind of like a semi-pyramidal membrane, right? And you put it into an isotonic solution, everything's going to be okay because the osmotic pressure inside and outside is going to be basically the same. And we're going to get flow in and out of the cell pretty equally. So nothing bad's going to happen to the cell. Typical isotonic solutions are 0.9% mass to volume saline or sodium chloride and 5% mass to volume glucose. So these are what are sort of considered isotonic solutions. Now, if you have a hypotonic solution, hypo means less than. That means that the pressure outside of the cell is actually less than inside the cell. So if you took that same red blood cell and you put it into a hypotonic solution, what's going to happen is, again, outside of the cell is going to be less concentrated than inside. So osmosis is going to kick off, and all the fluid from outside is going to rush into the cell in an effort to sort of dilute down the cell because it's more concentrated. The result of that is your cell is going to start to swell and probably burst, which is known as hemolysis, which is probably not a good thing. And bad things could happen in that case. So it will start to really swell as it kind of picks up all that and probably burst, maybe not out of the beaker there. Now, another type of solution is a hypertonic solution, and that means more than. So that means outside the cell is actually more concentrated than inside the cell. So if you pop that same red blood cell, maybe a new one, into a hypertonic solution, osmosis will kick in the opposite way. Now the cell's going to go, I need to go dilute down everything outside of me because it's more concentrated. And all of the fluid will rush out of the cell in that case in an effort to try to dilute down the outside of the cell. That's going to cause the actual red blood cell to start to shrink and go through crenation, which again, also not a good situation. Why, again, they give you an isotonic solutions for IV. So if you're getting an IV, you probably are not in maybe the best shape. So you don't want to give you something that's going to cause you more problems by screwing up your cells with the bad osmotic pressure. That is what these two are. To know whether it's hypo or hyper, it is as simple as it's either that number or less than or greater than those numbers will give you that hyper or hypotonic solution. Any questions on that there? So for example, here we can see isotonic solution. I like to call it the regular donut. Looks good, right? We have our hypertonic solution where everybody's going to run out of the cell and start to shrink, or donut hole. And then we have our hypotonic solution where everybody's going to run in and make the cell pop, jelly donut all over the place, right? So if I took a red blood cell and I put it in the following solutions, I put it into 0.9% 0.9% sodium chloride. I put it into 12% glucose. I put it into pure water. I put it into 0.1% sodium chloride. For each of them, what will happen to the red blood cell? Will it shrink? Will it swell? Will it be okay? We'll go through crenation. Take a moment there for each of those and decide. Okay, so let's take a look. So put my red blood cell into 0.9% sodium chloride. I am going to be okay because 0.9% is an isotonic solution. And so is, again, 5% glucose. So those two numbers are kind of important to remember. So we're going to be okay here. We're going to have equal osmotic pressure in and out of the cell there. So we're going to have nice equal flow in and out. If I put it in a 12% glucose solution, 12% is definitely higher than 5. So that's going to make that a hypertonic solution. And that again means that outside my cell is more concentrated than inside. And that's going to cause my cell to try to dilute it down. That's going to cause it to shrink and go through crenation in that case. We have 0.1% sodium chloride. 0.1% is less than 0.9. So that is a hypotonic solution. And again, in a hypotonic solution, outside the cell is less concentrated than inside. So this is going to cause everybody to rush into the cell in this case, going to cause it to swell and go through hemolysis and burst. Lastly, pure water. Pure water, reminder, has no osmotic pressure, which means this is a case where water would not be good because this is actually hypotonic. And if you put it into pure water, you're going to get kind of the same deal. Outside the cell is going to be less concentrated, so it is going to cause everybody to rush into the cell and start to swell in this particular case. Any questions on any of those there? Now, dialysis is a similar process. Dialysis allows small molecules and ions as well as solvent molecules to pass through, but it does retain as large particles like colloids. We use dialysis, right, to filter out in our body certain things we don't want. You could also do it in the laboratory in a dialysis bag, which again, in the bag, even though you might not be able to see it, there is holes in the bag which allow certain size molecules to come out of the bag and keep other ones in there. Sometimes people, for example, if they're doing any type of protein, say purification or examination, maybe that protein in the body normally is at a specific pH, and maybe you want to analyze your protein at that pH, so you could put it into like a buffer solution at pH, let it kind of sit there in a dialysis bag. Protein's too big to escape, so it's just going to sit in the bag and kind of equilibrate to that same pH. Then you could kind of do your experiment with it. All right, any questions on that? That is chapter 10, which is the last chapter on our exam, which is Tuesday. Yes. Chapter of the season here. So we're going to talk a little bit about it, and then obviously I'll let you know what, if anything, will be on the final exam from this chapter. But kinetics deals with the rate of reactions. And chemical kinetics is really the study of how fast or slow a reaction takes place. It is not to be confused with equilibrium, which if you're going to take 200B, that's pretty much all you talk about, or we talk about in 200B, which is equilibrium. But kinetics really deals with how fast or slow a reaction takes place. It also is different than something else you'll talk about 200B, which is thermodynamics, which is whether or not a reaction is spontaneous or not. And sometimes people think about spontaneous reactions as happening really fast because they hear the word spontaneous. And as you'll learn in 200B, when we talk about a reaction being spontaneous, it has really nothing to do with how fast or slow the reaction takes place. It just has to mean that that reaction would take place under normal conditions in if you just left it alone without any type of interruption. The rate of a reaction, or the kinetics, deals with how fast or slow it does take place. So let's talk a little bit about sort of kinetics. And kinetics, for example, if we have a reaction of A going to B, we do look at the reaction rate, and very commonly what we look at is the change in the concentration over a period of time. So very commonly in kinetics, rates are given to you in molarity per second, molarity per minute, per hour, some type of change in the concentration of a reactant or a product with time. If we look at this reaction, we would assume over time that our reaction is heading towards the product side. And in order to make our products, we would need the amount of our reactants to decrease with time, and our products would increase with time. So we would expect these guys to decrease with time. And we would expect, obviously, our products to increase with time. Now, we could write what is sometimes referred to as the rate expression. And it expresses basically the change in the concentration of a reactant or product with time. And the rate is equal to minus the change in the concentration of A versus the change in time. When you see these little brackets, these mean concentration. And typically that is molarity, which is moles per liter is what we're talking about when we see that. The delta is change. Yeah, so that means change basically. So for our products, because it's increasing with time, we have the change in the concentration of B over the change in time. We actually do not have a negative there because it's actually increasing with time. The reason the negative is here is because when you calculate the rate of a reaction, or the average rate of a reaction, it should end up being a positive number. So the rate that you calculate should end up being a positive number. So why do we need the negative with our reactants? Well, let's just take a look at this reaction here. If we want A to B, and we initially had 4 moles or 4 molar of A, and nothing of B. And at the end of the reaction, maybe we ended up with 1 molar of A and 3 molar of B. So if we were to calculate the change in the concentration of A, you would take your final concentration of A minus your initial concentration of A. And if you do that, you will end up with 1 minus 4 in this case, are negative 3 molar. And that negative is counteracted by the negative in this formula to end up with a positive rate here when we do that. Now, we don't need the negative on the product side, because if you did the change in the concentration of B, which would be the final concentration of B minus the initial concentration, you will end up with 3 minus 0, which is positive 3 molar, which will give us a positive value here. So when you write a rate expression for a reactant, you do have the negative there to basically make sure that you do end up with a positive overall rate for that reaction, because the change in the concentration should end up being negative, because it should be decreasing with time, while on the product side, you don't have to worry about that, because you actually should end up with a positive value for the change in the concentration of that product. Any questions on that there? Now, how do we follow kinetics, or what do we see in kinetics? And a lot of kinetics is about graphs and looking at graphs and watching things over time. Obviously, here we could visually see that at the very beginning of the reaction, all we have are reactants. We have no products, as those reactant circles, black circles represent our reactants, products represented by red circles here. Not until the reaction begins, we start to see some appearance of red circles. And obviously, as we continue towards our products and the end of the reaction, we have a lot more product than we do reactants. And that's what we see here. At time 0, it's all reactants, no products. And as we start to use up our reactants to make products, we'll start making products. And at some point, we will obviously start to decrease a lot of reactants and we will make a lot more products. Eventually, the reactants will start to deplete itself and you will kind of slow down the reaction. You're not going to make as much products, right? Because the availability of reactants are now going to be much less than where it started with. And it's going to take longer for everybody to kind of come together to make products, and it's going to slow down very much. At the very beginning of the reaction, there's a ton of reactants present. So it doesn't take a long time for them to find each other and kind of kick off the reaction and start making products. But as you start using up your reactants, the pool of reactants gets smaller and smaller. It can take longer for them to continue to make products. One of the ways that we can figure out, how a concentration is changing during times is through a kinetics experiment where if we have somebody in the reaction, either a reactant or a product that has a color associated with it. So for example, Br2 is right there, that color. And as you go to the product side, we're pretty much colorless over here. And as you can see in the beaker here, over time, we're starting to deplete our reactants and we're ending with products. Having something that has color is really good because you could use something like we did in our favorite experiment ever, the Kool-Aid experiment. We could use our Spec 20 and do some spectrophotometry where we have a detector, a light source that we shoot waves at a specific wavelength, and we can measure absorbance. And as you know, when you did that experiment, one of the things that you tried to figure out was what is the good wavelength to set your spectrophotometer to, and you want to set it to the maximum absorbance. And that way all your samples are good. And that's what do you call it? The spectrometer master or something did, right? At different wavelengths. And you pick the one that had the highest absorbance. Again, we want to do that because all of our samples can absorb all the way up here. Again, if we pick over here, we're in trouble because that's about all the absorbance we're going to get is that little bit on the side. Remember as well, right, the color that we see is the complementary color to the wavelength being absorbed. So again, even though our solution may have been red, like in that experiment, we did not actually set our wavelength to the red wavelength visible part of the spectrum. We actually set it more to its complementary color of red. So the absorbance is proportional to the change in the concentration of Br2. Remember, the darker the color of the solution, the higher the absorbance you're going to have. So in this particular reaction, we actually should have a lot of absorbance at the beginning because it's very much colored solution. But at the end, we should start to see our absorbance start to decrease and drop down. And that is proportional to the amount of Br2 that is present. So at the higher concentrations, we should see higher absorbance values. And as the concentration of Br2, which is the only thing that's causing the color, starts to come down, so should the absorbance values. Now remember as well, we can look at that, and we could also look at two types of rate. We typically like to look at the average rate versus an instantaneous rate. So kind of the difference between average rate and instantaneous rate is the average rate is kind of the rate for the overall reaction from kind of like beginning to end, if you will. The instantaneous rate can be for a specific period of time. So for example, I like to illustrate it as like when you're driving. For example, if you're driving from here to Arizona, along the way, maybe at certain points you're doing 55, 60, 65, 75, 80, 85, 90-ish. Hopefully no cops behind you at that point. Drive safely out there. It is raining currently. But if you averaged out your entire trip from beginning to end, maybe you only drove about 72 miles per hour for on average the whole way. But at some points along the trip there, you're going to go slower, right? At some points, you're going to go faster. So if you just looked at it like a window of time, that would be your instantaneous rate. And the same thing happens with reactions. For example, as I just mentioned, at the very beginning of the reaction, because there's so much reactants available, you're going to have a pretty good rate happening at the very beginning of the reaction because they're going to be able to find each other really quick and start reacting. As that reactant molecules get depleted, it's going to maybe take a little bit longer for those guys to start reacting towards the end of the reaction. And again, on average, from beginning to end, you could have an average rate that may look very different if you just kind of looked at a period of time between it. You can do that graphically, which clearly we're not going to do, but you can take the slope of the tangent of that line and you can figure out an instantaneous rate for a particular period of window. And here's that sort of experiment we've been talking about. And there is, if you look at sort of the data from that experiment, there is a value that actually is a constant value. And that comes from this, what is known as a rate law. And this guy right here is what is known as the rate constant. And it actually is lowercase k, not to be confused with 200B's topic of the season, capital K, which is the equilibrium constant. Yeah. So there actually is a difference in the two K values there. This is not in this chapter. Lowercase k is typically the rate constant. There is a relationship really between the rate constant and the equilibrium constant, but again, that's a difference here. So you can see that if you actually solve for the rate constant by taking the rate constant is equal to the rate in this particular example divided by the concentration of Br2 by dividing that to the other side, you will see here you do get a relatively constant value. The rate constant you could kind of think of as how fast or slow the reaction takes place. You can just kind of see it in this sort of rate law here. Basically, if this number gets larger, so does the rate of that reaction, obviously, because you're going to multiply it. If this number gets smaller, then your rate's going to get a little bit slower as well. So it does have sort of a direct, and you can kind of think of it as sort of applying to how fast or slow a particular reaction may take place. Now, what happens if you have a reaction where there really is maybe no color? And we could have a reaction like this where everything is colorless, except for the fact that they put a little bit of yellow dye in there so you can actually see it in the picture. But it is kind of colorless here. But in this particular case, we are generating a gas here in this particular reaction. And when we think of gases, obviously we think of the ideal gas law. And something that we did solve for with the ideal gas law, which again is N over V, which equals P over RT. And once again, N over V is moles over liters. So once again, that is a way to figure out the molarity of a gas. So you could actually do a kinetics experiment involving a gas by following the pressure here. In this particular reaction, the only gas presence on the product side, which means you're not going to see pressure until you start making some oxygen gas. So as soon as you start making oxygen gas, then you know this reaction is actually going to the product side and you're actually having this reaction take place. So you could put that into a rate expression and you will end up with something like this where R is a constant. If you did this reaction, the temperature would be a constant. So basically, if you just follow over time the change in pressure, that will also relate basically to the change in the concentration of the gas. In this case, we would actually start to see the pressure start to increase as we start making products rather than obviously decreasing in this case. So this is another way that you could kind of do a kinetic study where perhaps maybe you don't have anything that has a color that you could do spectrophotometry on. Here you could follow the pressure, which will allow you to figure out what's happening in that reaction. Now, when we look at a reaction, as we know from our favorite things, which is stoichiometry, we always have to sort of take into account the stoichiometry of a reaction and how it is reacting. And in this particular case, if we look at our coefficients, we see that for every 2 moles of A, we do produce 1 mole of B. So with kinetics and rates, we do have to take into account the stoichiometry of the reaction. And we could do that like we see here. The rate is equal to negative because A is a reactant. So again, should be decreasing with time. we actually go 1 over the coefficient. So if you take 1 over the coefficient, which in this case is 2, that will actually wrap together for you the mole-to-mole relationship and the kinetics sort of calculation together without having to do them separate. So if you take 1 over the coefficient, that will do that. That's the change in the concentration of A over the change in time. We could also do it for our product. The rate is equal to, the coefficient here is 1, which basically gives us 1 over 1, which is 1, which is why there is no number written there, basically. It's because it's 1. And it's also a product, so it should be increasing with time, which means we should have a positive sign there, so no negative either. The change in the concentration of B with the change in time. In general, for a reaction, you could basically do that rate expression for everybody in this reaction. So the rate is equal to minus 1 over the coefficient of A. Change concentration of A over change time equals 1 over the coefficient of B. Minus change concentration B over time. Again, on our product side, we end up with positive values here, 1 over the coefficient of C and 1 over D as well. What this allows you to do with the rate expression is you simply just need to know one piece of information about somebody in the reaction. If you know the average rate, you can then figure out how everybody is changing with time, reactants, products. If you know how one reactant is changing with time, you can figure out how all the other reactants are changing with time, how all the products are changing with time, and vice versa as well. If you know a product, you can figure out everything else there. You can put them all together. You could just isolate the ones that you're interested in. So maybe we're interested in our reactants here. We could have this guy and this guy. Now, how are these two related to each other? Well, if you're able to figure out the rate of this guy, that is the same number. So now you know this guy, and it can allow you to figure out how that guy, that second reactant there, is changing with time. So you can kind of use them, those relationships, and tie one thing to the next. Any questions on that there? So why don't you take a second here and write the rate expression for this reaction, all the ones that are related here to each other. All right, so let's take a look. So we'll start here. The rate is equal to, we'll start with our first reactant. Again, because it's a reactant, we're going to go with negative the change in the concentration of CH4 over the change in time. Here, basically, our coefficient is 1, which means we would have 1 over 1, so you don't really need to put the 1 here for it. That would equal our second guy, which is negative because it's a reactant. It does have a coefficient of 2, so we'll do 1 over our coefficient. And again, that's going to take care of all the kind of stoichiometry part of it, the change in the concentration of O2 over the change in time. This will now come to our product side, which coefficient is 1. This is also going to be positive, so this is just going to be the change in the concentration of CO2 over the change in time. And lastly, we do have a coefficient of 2 here, also positive. So 1 over our coefficient takes care of the stoichiometry, change in the concentration of water over the change in time. Once again, you can use this if you just knew one piece of information to figure out how everybody else is changing. Any questions on that there? All right, so let's take a look at one where maybe we do have a piece of information just to see how we can kind of do this calculation. Let's say for a given reaction, the concentration of I minus changes from 1 molar to 0.868 molar in the first 10 seconds. We want to calculate the average rate in the 10 seconds and what is the concentration of H plus over time, basically how H plus is changing with time. So when you have a problem like this, you really don't need to think about everybody's relationship here. You really should just pull out the rate expression for each thing you're interested in. So clearly one thing we're interested in is I minus, because that's the information we have. So if I look at I minus, I see it's a reactant. So I could write that the rate is equal to negative because it's a reactant, 1 over the coefficient, which is a 3, the change in the concentration of I minus over the change in time. The other thing we're interested in is obviously H plus. And if we look at H plus, it also is a reactant. And that would mean that the rate for H plus is equal to negative 1 over the coefficient, which is a 2. The change in the concentration of H plus over the change in time. So these are really the only two we're kind of interested in this problem. And the information we have is the initial concentration of I minus is 1 molar. We have our final concentration of I minus, which is 0.868 molar. If you want to do time, our final time, our initial time would be 0 seconds. Our final time would be 10 seconds in this case. So that's going to give us everything we need to calculate right here. So we'll put it into our first rate expression for our I minus, minus 1 over 3. Again, we're going to do final minus initial here. So that's going to be 0.868 minus 1 molar divided by 10 minus 0 seconds. Once again, this subtraction is going to give us a negative number. And that, once again, is why we have the negative out in front, so that our rate will become a positive. We'll go 0.868 minus 1 divided by 10 and divided by 3 will give us a rate, our average rate for this reaction of 0.0044 molar seconds, as the units do not cancel here. So that is the rate. First off, any questions on that part of the calculation? Why that number is important is ultimately in this problem, we are looking for that, which is the average rate. So that is the average rate right there. But we are also looking for what is the concentration of H plus over time. And that average rate that we just calculated is also this number right here. It is the same number. So those two guys are the same number. So by calculating that, we now know the rate for our other guy is going to be the same. We have that. So now we could actually solve for what's missing. That would give us here 0.0044 molar seconds equals minus 1 over 2 change in the concentration of H plus over the change in time. We're going to basically move this to the other side, which basically means we're going to multiply 2 to the other side. But it's not just a 2, there's also a negative that needs to be multiplied as well. So we're going to multiply the negative 2 to the other side. And if we do that, obviously here, we're going to end up with minus 0.0088 molar seconds is how the concentration of H plus over time is changing. Now, this does make sense, right? A couple of things. It is actually a negative rate for this guy, and that's okay because he's a reactant, which means he should be decreasing with time, which is why we do end up with a negative number here. And we also see what we were talking about a second ago. Not all reactants are reacting the same rate, right? On average here, our H plus is decreasing twice as fast as the overall average rate of that reaction, right? So, and that makes sense as well. It's a reactant, so it's going to start reacting pretty quickly. So it's actually reacting a lot faster than the average rate of this reaction. Any questions on that there? Okay. All right, so let's take a look at another one here. All right, let's say we had 2.4 times 10 to the 2 grams of NOBr with a molar mass of 109.91 grams per mole, which you would get obviously from the periodic table if it wasn't given to you. It decomposes in a 200 milliliter flask in 5 minutes. We're looking for the average rate of Br2 production. So once again, I'm just going to be concerned myself with the two things in the problem. I'm going to write a rate expression from the equation for my first one, which is minus 1 over 2 because of the coefficient, and it's a reactant, so it's going to be decreasing with time. The change in the concentration of NOBr over the change in time. And now for my Br2, the rate is equal to positive 1 over 1, the change in the concentration of Br2 over the change in time. So we're going to start with our NOBr, since that's the information we have. We are looking for the change in the concentration of NOBr. That's basically the molarity. So we need to calculate the molarity here. So I'm going to take my 2.4 times 10 to the 2 grams of NOBr. I'm going to use the molar mass that they nicely gave to me, 109.91 grams per mole. And we're going to end up with 2.4 to the 2 divided by 109.91. That's going to give me 2.184 moles of NOBr. Molarity is also moles per liter. So there's my liters right there. That's 200 milliliters converted to liters. 1,000 milliliters is a liter. Gets you 0.2 liters. So we're going to take this guy here, divide it by 0.2 to convert it into liters. And that's really going to give us the concentration change of 10.92 molar. So that is the top part here. I am interested in the rate of Br2 in molarity per second. So just to get my minutes into seconds, I'm going to convert that to seconds so everything's in the right units. At some point, you would need to convert the minutes into seconds, so might as well just do it up front. So obviously in a minute, there's 60 seconds, I hope. And that's going to give us 300 seconds. So now we have the time component and we have the concentration. We could stick that in. The rate's going to be minus 1 over 2, negative 10.92 molar. I did negative because I need my guy to end up positive. And this is a reactant, so the change should be negative in the concentration, divided by our 300 seconds. That's going to give us 10.92 divided by 300 divided by 2. It'll give us a 0.0182 molar seconds as our average rate. So again, this is going to help us with what we're really interested in, which is this guy. And we could see by looking at that rate expression that the rate is equal to change in concentration of Br2 over the change in time. And frankly, there's our answer right there, since that is equal to the rate, 0.0182 molar seconds would equal the change in the concentration of Br2 over the change in time. So in this particular case, the Br2 is basically changing the exact same rate as the average rate of the reaction. And again, it ends up being positive for that guy because he's a product, so he should be increasing with time. And in basically every second, his concentration increases by 0.018 molar, basically, as we go through this one. Any questions on rate expressions here? Yeah. All right. So last thing we're going to talk about here for tonight is a couple of factors that affect the rate. And again, we've talked about some of this as we were going through these last few examples. Obviously, the nature of reactants are going to have a big effect on the rate. Smaller molecules tend to react faster. Gases, because they have a lot of energy, are constantly moving around, which means they're good to go and react a lot quicker. They also, when they react, have a lot of energy that allows them to actually get the reaction to actually proceed. Liquids are slower than gases, and typically solids are slower than everybody because they're just sitting there. If you have a solid, more surface area is better for reaction, kind of like that magnesium strip we were doing in that experiment. Like I said before, if you kind of coiled it really tight, there's no surface area for the acid to get to. It's going to take forever for it to react with it. As we talked about, there's an activity series of metals. Some that are higher on the list are more reactive than lower on their list. That's what we talked about with single replacement reactions that occur. Ions are also react very fast because ions are typically found in solution floating around, ready to go, basically. So they're good to go as they're floating around in the solution. Temperature is a huge factor in terms of the rate of the reaction. Typically, if you increase the temperature, everybody has a lot more energy to get to the product side. It allows everybody from the reactant side to get up over an energy hill to get to the other side. And if you raise the temperature about 10 degrees Celsius, that's usually enough to double the rate of the reaction. Opposite is true, obviously, if you slow down a reaction, you could do so by like throwing everybody on ice and lowering the temperature. When you do that, everybody loses energy and no longer has the will to react. A catalyst is also a very common way that we speed up a reaction. A catalyst is not a reactant. It is not a product. It is there simply to allow the reaction to occur faster, and it does not get used up. Again, a lot of times you can find a catalyst written on top of the arrow in a chemical reaction. For example, there could be a catalyst that is a solid catalyst, and if you had gas molecules, that can maybe be an attraction point for those gas molecules to come to. And what that does is it allows those guys to now be in very close proximity to each other, and that's going to allow them to start reacting really quickly. Rather than if the catalyst wasn't there, they just got to fly around and hope to sort of come in contact with each other. So a lot of times a catalyst can sort of act that way. Sometimes we need a catalyst like the environment needs to be correct, like a pH. So sometimes we use acid as a catalyst or something like that to sort of get everybody in the right pH sort of range for things to work. Catalyst could be homogeneous, just like everything's reactant, same phase. It can also be heterogeneous as well. Lastly here, the concentration is really an important factor. Like if you had molarity, that is moles per liter, that is moles of solute. So the larger the molarity you have, the more solute you have in that solution. It is actually the solute that is reacting. It's the stuff floating around in the solution. So the greater the concentration, the more stuff you got floating around the solution. Again, just by proximity of more things in there, they're pretty much going to come in contact with each other a lot faster than they would if there was a less amount in there. Gas concentrations depend on partial pressures. The higher the pressure, the higher the concentration. That also means when we talk about Boyle's law, right? Higher pressure, smaller volume. Everybody's much closer to one another. They don't have as far to travel to come in contact, and that should increase the rate of the reaction.